The idea that homes must constantly consume energy is actually a surprisingly recent belief. For most of human history, a house that required constant fuel to stay comfortable would have been considered pretty poorly designed. Long before gas furnaces, electric heaters, or central air systems, entire civilizations built homes that regulated temperature almost automatically. Stone walls stored the warmth of the day. Earth sheltered buildings from harsh winds. Carefully placed windows captured the winter sun and rejected the summer heat. These weren't just primitive improvisations. They were deliberate architectural systems, all based on observations about sunlight, air movement, and the way materials store heat. Greek philosophers wrote about them. Roman engineers refined them. Persian builders used them to store ice, even in desert climates that regularly exceeded 45 degrees Celsius. Yet today, many modern homes require continuous heating or cooling just to remain livable. The question really isn't whether self-heating homes are possible. History shows they've existed for thousands of years. The deeper question, honestly, is why those ideas were largely abandoned just as modern industry began selling the machines that replaced them. Greek thinkers were already describing the principles of passive solar homes. In fact, the earliest surviving discussions of self-heating houses appear in ancient Greece. Around the 4th century BCE, the philosopher Socrates described what he considered the ideal home design. His explanation was, surprisingly, pretty practical. A house, he argued, should face south so that the winter sun could shine directly into the interior. In summer, when the sun rises higher in the sky, roof overhangs would cast shade and prevent overheating. This concept, now called passive solar design, relies on simple geometry. The angle of the sun changes with the seasons. A building designed around that fact can regulate its own temperature far more efficiently than one that ignores it. Greek builders also understood the importance of thick masonry walls. Stone and clay absorb heat slowly during the day and release it gradually at night. In winter, this stabilizes indoor temperatures. In summer, it prevents daytime heat from penetrating the interior. Modern engineers call this thermal mass. Greek architects didn't use that term, but they understood the behavior of the materials they worked with. Entire neighborhoods were laid out so that homes would not block each other's access to winter sunlight. The goal was simple: design the house so nature did most of the work. Roman engineers expanded these ideas into large-scale heating systems. The Romans inherited many Greek architectural principles and pushed them further. One of their most impressive innovations was the hypocaust, a system used to heat baths, villas, and public buildings across the empire. Instead of warming rooms directly with open fires, Roman builders raised floors on small pillars. Hot air from a furnace traveled through the space beneath the floor and up hollow channels in the walls. The masonry absorbed the heat and released it slowly into the rooms above. This allowed enormous structures to maintain stable temperatures using relatively small fires. The baths of Caracalla in Rome covered more than 25 acres and could accommodate thousands of visitors daily. Yet their heating relied on the same principle Greek builders had recognized centuries earlier: warm the mass of the building itself, and it will regulate the interior climate. Roman engineers also paid careful attention to solar orientation. South-facing windows captured winter sunlight, while courtyards and shaded porticos controlled airflow. These buildings were not energy-free, but they required far less fuel than systems that heat air directly. The structure itself became part of the heating mechanism. Persian builders solved an even harder problem: preserving ice in the desert. If Greek and Roman builders demonstrated how to capture heat, Persian engineers demonstrated how to resist it. Across Iran and Central Asia, large domed structures called yakhchals stored ice throughout the year in climates where summer temperatures regularly exceeded 40 degrees Celsius. The word literally means ice pit. These structures combined several sophisticated techniques. Thick walls made from a mixture of clay, sand, and ash provided extreme insulation. Underground chambers reduced exposure to daytime heat. Tall wind catchers directed cool night air downward into storage spaces. But the most remarkable feature was their use of thermal mass and evaporation to create natural refrigeration. During winter nights, shallow pools of water outside the structure would freeze. Workers cut the ice into blocks and moved it into the insulated chamber below the dome. Once sealed inside, the thick walls and carefully controlled airflow kept the ice from melting even during the hottest months. The design relied entirely on physics that builders had learned through centuries of experimentation. No compressors, no electricity, no modern refrigeration, just an understanding of heat, mass, airflow, and sunlight. The physics that made these buildings possible is straightforward and well understood. At the heart of all these systems lies the concept of thermal mass. Materials like stone, adobe, brick, and packed earth absorb heat slowly and release it slowly. When sunlight warms a thick wall during the day, that energy becomes stored within the material itself. Hours later, as outdoor temperatures drop, the wall releases that stored warmth into the interior. This process can stabilize indoor temperatures with remarkable effectiveness. Modern laboratory testing has confirmed what ancient builders already understood through experience. Buildings with high thermal mass and proper solar orientation can maintain comfortable temperatures with dramatically reduced external heating. In climates with strong sunlight and cool nights, the effect becomes even more pronounced. The building itself acts like a battery for heat. A French scientist quietly revived the concept in the 20th century. Although industrial heating systems dominated the 20th century, a few researchers continued studying passive solar design. One of the most influential was the French engineer Félix Trombe. In the 1950s, Trombe developed a simple wall system designed to capture and store solar heat. A dark masonry wall was placed behind a sheet of glass with a narrow air gap between them. Sunlight passed through the glass and warmed the wall. The wall absorbed the heat and slowly released it into the building over the following hours. Small vents allowed warm air to circulate naturally between the wall cavity and the interior. This design became known as the Trombe Wall. It required no pumps, no electronics, and no fuel. The only energy input was sunlight. Thousands of experimental homes built in the 1960s and 70s used this approach with impressive results. In many climates, a properly designed Trombe wall could supply the majority of a home's winter heating. The concept was not revolutionary. It was a modern version of what Greek and Roman builders had practiced centuries earlier. An unconventional architect pushed the idea even further in the American Southwest. While researchers studied passive solar heating in laboratories, a young architect in New Mexico began building entire houses around the concept. Michael Reynolds believed modern homes had become unnecessarily dependent on outside infrastructure. His solution was a type of building he called the Earthship. Earthships use discarded automobile tires packed tightly with earth to create massive walls. These walls provide extraordinary thermal mass. The buildings are typically partially buried into hillsides, using the surrounding soil as insulation. Large south-facing windows allow winter sunlight to penetrate deep into the interior. The thick earth-filled walls absorb that heat and release it slowly overnight. In summer, roof overhangs block the high sun while natural ventilation carries warm air out of the structure. Many Earthships also include rainwater collection systems, solar electricity, and indoor greenhouses that help regulate humidity. In the high desert climate of New Mexico, these homes can maintain stable indoor temperatures year-round, with little or no external heating or cooling. Some of the earliest Earthships built in the early 1970s are still operating today. The resistance these ideas encountered did not come from physics. Technically, none of these concepts violated modern engineering standards. The difficulty was regulatory and economic. Building codes in most countries were written around conventional construction methods. They assume houses will rely on standardized heating and cooling systems. When architects attempted to submit designs that did not include those systems, regulators often had no category under which to approve them. Financing created another obstacle. Mortgage lenders and property appraisers typically evaluate homes based on familiar features, square footage, finishes, appliances, and location. Energy independence rarely fits easily into those formulas. A house with extremely low operating costs might not receive higher appraised value if its design differs from typical construction. This created a paradox. Homes capable of drastically reducing energy consumption often struggled to gain approval or financing precisely because they departed from the models the system was built around. Yet the science continued advancing quietly in the background. Despite those obstacles, research into passive building design never disappeared. Universities in Europe and North America conducted long-term studies on insulation, air sealing, and thermal mass. Engineers refined methods for capturing solar heat while minimizing unwanted heat loss. By the late 20th century, these ideas began converging into a new standard known as the passive house. Passive house buildings are designed so efficiently that they require up to 90% less heating energy than conventional structures. Thick insulation, airtight construction, high-performance windows, and careful solar orientation work together to maintain stable indoor conditions. Thousands of these homes now exist across Europe, North America, and Asia. Many require only small supplemental heaters to remain comfortable even during winter. In effect, they operate on the same principles ancient builders understood: capture the sun, store the heat, and prevent it from escaping. What these forgotten building traditions reveal about technology and progress is pretty eye-opening. Looking across this long history reveals an uncomfortable truth. The challenge of heating and cooling buildings was largely solved long before modern mechanical systems even existed. Greek philosophers, they recognized the importance of solar orientation. Roman engineers used thermal mass to stabilize those enormous public buildings. Persian architects, they preserved ice through desert summers using passive cooling. Then, 20th century scientists confirmed all this physics in their laboratories, and modern experimental builders have shown that homes can actually operate with minimal external energy. None of these ideas were really mysterious. They were just overshadowed during a century when cheap fossil fuels made mechanical heating systems way easier to install than thoughtful architecture. Once buildings became dependent on those systems, entire industries grew around them. Furnaces, air conditioners, ductwork, and all the infrastructure that powers them. Changing that pattern, honestly, requires rethinking how buildings are designed from the ground up. The lessons from these overlooked designs are increasingly relevant again. Energy prices rise and fall, but the underlying physics never changes. Sunlight still reaches the earth every day. Stone still stores heat. Earth still insulates. Architects and engineers are once again studying how buildings can work with those natural forces, rather than constantly fighting them. In many ways, the future of efficient housing may look surprisingly familiar to the past. Thick walls, careful orientation, thoughtful use of sunlight and shade. Ideas that were once considered ancient are now being rediscovered as practical solutions. Understanding these forgotten innovations reminds us that, honestly, history often holds the solutions we need. Technological progress is often portrayed as a straight line moving forward. But the history of architecture actually shows a different pattern. Knowledge is sometimes lost, rediscovered, and refined across generations. Self-heating houses were never impossible. They were just overshadowed during a period when energy was cheap and convenience came first. As energy systems evolve and environmental pressures grow, the lessons preserved in ancient buildings, experimental architecture, and modern passive design may become increasingly important. Because sometimes the most effective technology is not the newest invention. It is the knowledge that was quietly waiting in history all along. If you value stories like this, stories that uncover the overlooked ideas that shaped our world, subscribe to Hidden in History. And if you found this exploration worthwhile, share it with someone who appreciates the deeper side of history.